On June 24th, 2025, astronomers at the Atlas Observatory in Chile detected a faint point of light moving through the sky on a trajectory that immediately stood out as unusual. Within days, follow-up observations from telescopes around the world confirmed what the initial data suggested. This object was not from our solar system. It was moving on a hyperbolic path, an open arc that meant it came from interstellar space and would eventually leave the same way, never to return. It was designated 3I Atlas, the third confirmed interstellar object ever detected passing through our cosmic neighborhood. I'm hosting Space Horizon, where we cover space discoveries the way working scientists actually discuss them. By the end of this video, you'll understand exactly what 3I Atlas did during its passage through the inner solar system that no other comet, interstellar or otherwise, has ever been observed doing. You'll learn what that behavior tells us about where this object came from and why it matters for our understanding of planetary systems beyond our own. Let's start with what makes an object interstellar. Every comet and asteroid in our solar system orbits the sun in a closed loop. They might take decades or even millennia to complete one orbit, but eventually they come back. Their orbital eccentricity, the number that describes how stretched their orbit is, ranges from 0 for a perfect circle up to just under 1 for extremely elongated ellipses. When an object has an eccentricity greater than 1, the math changes. The orbit is no longer closed. It's a hyperbola, a path that brings the object in from infinite distance, swings it around the sun once, and sends it back out to infinite distance on the other side. That kind of trajectory only makes sense if the object originated somewhere else, beyond the sun's gravitational influence, and is just passing through. 3I Atlas had an orbital eccentricity of approximately 6.1 when astronomers calculated its path. That's the most extreme hyperbolic trajectory of any interstellar visitor ever confirmed. For comparison, Oumuamua, the first interstellar object detected back in 2017, had an eccentricity around 1.2. Borisov, the second interstellar object found in 2019, came in at about 3.4. 3I Atlas was moving through the solar system on the least gravitationally bound, most aggressively outbound path of any object we've tracked. At the time of discovery, it was already traveling at roughly 137,000 miles per hour relative to the Sun, and it was still well outside the orbit of Jupiter. That speed alone indicated this wasn't a local object. Solar system comets get accelerated by gravitational interactions with planets, but they don't arrive from the outer solar system already moving that fast. Something else had given this object its velocity long before it ever encountered our Sun. Within weeks of discovery, multiple observatories turned their instruments toward 3I Atlas to gather as much data as possible before it passed through the inner solar system and receded beyond reach. Hubble observed it in August 2025. The James Webb Space Telescope was allocated observation time in October. Ground-based telescopes across 3 continents coordinated campaigns to monitor its brightness, its spectrum, and any changes in its activity as it approached the sun. And that's when things started to get unusual. Most comets, when they get close enough to the sun for solar radiation to heat their icy surfaces, begin to outgas. Frozen water, carbon dioxide, methane, and other volatile materials sublimate directly from solid to gas, venting into space and forming the fuzzy cloud called a coma that surrounds the nucleus. That outgassing also produces a tail, pushed away from the sun by solar wind and radiation pressure. The closer a comet gets to the sun, the more active it becomes. The coma expands. The tail grows longer. The brightness increases. 3I Atlas did something different. As it approached perihelion, its closest point to the sun in late October 2025, its coma developed normally. Water vapor, carbon dioxide, and traces of methane were all detected venting from the surface, exactly as expected. But the tail didn't behave the way comet tails normally do. Instead of one continuous tail stretching away from the sun, 3I Atlas developed multiple distinct streams of material, ejecting in different directions. High-resolution images captured by the Gemini North Telescope in Hawaii showed at least 4 separate jets of gas and dust erupting from different points on the comet's surface. Each jet had its own trajectory, its own brightness, and its own chemical composition when analyzed spectroscopically. One jet was dominated by carbon dioxide. Another showed higher concentrations of water vapor. A third contained unusually high levels of organic molecules, complex carbon-based compounds that don't normally appear in such abundance in comet outgassing. This kind of asymmetric, multi-directional outgassing has been observed before in solar system comets, particularly those with irregular shapes or active surface features like geysers. What made 3I Atlas unusual was the persistence and intensity of the jets. They remained active for weeks, venting material at rates far higher than models predicted for an object of its estimated size. Researchers led by Dr. Martin Cordner at NASA Goddard Space Flight Center used the James Webb Space Telescope to analyze the chemical fingerprints of the outgassing in detail. What they found added another layer to the puzzle. The ratio of carbon isotopes, specifically carbon-12 to carbon-13 in the venting gas, was significantly different from what's measured in solar system comets. The ratio suggested this ice had formed in an environment with less carbon-13 available, which corresponds to an earlier era of galactic chemical evolution. Working backward through models of how the Milky Way's chemistry has changed over time, Cordner's team concluded that the ice in 3I Atlas likely condensed somewhere between 10 and 12 billion years ago. For context, our solar system is 4.6 billion years old. This comet was carrying ice that froze before our sun even existed, in a region of the galaxy that was chemically distinct from the neighborhood where Earth eventually formed. That finding was published in the journal Nature in June 2026 and immediately generated significant attention in the planetary science community. It meant that 3I Atlas wasn't just a visitor from another star system. It was a visitor from another era of galactic history, carrying material that formed during what astronomers call cosmic noon, a period roughly 10 to 12 billion years ago when star formation across the galaxy was at its peak. But the chemical analysis revealed something else, and this is where the story gets genuinely strange. In addition to water, carbon dioxide, methane, and the expected simple molecules, Webb detected absorption features in the infrared spectrum that didn't match any compound in the standard Comet chemistry databases. The features appeared at wavelengths around 3.3 and 3.4 micrometers, the range where you'd expect signatures from complex organic molecules, but the specific pattern didn't correspond to any of the simple hydrocarbons that normally form in cometary ices. The research team described the unknown features as consistent with long-chain carbon molecules, possibly aromatic hydrocarbons or more complex organic polymers. These are the kinds of molecules that can form naturally in certain environments, including dense molecular clouds where stars are born and the surfaces of icy bodies exposed to radiation over billions of years. But finding them in such high concentrations in active outgassing from a comet was unprecedented. Separately, another team using the Very Large Telescope in Chile detected something even more puzzling. In October 2025, during one of 3I Atlas's most active outgassing periods, they identified emission lines corresponding to nickel vapor. Nickel in comets isn't unknown. It's been detected before in a handful of solar system comets and even in Borisov, the previous interstellar visitor. What made this detection unusual was what was missing. Every previous observation of nickel in a comet had been accompanied by iron, because the two metals are forged together in dying stars and typically travel through space bound to each other in dust grains. In 3I Atlas, the nickel signal was strong and clear. The iron signal was nearly absent. That shouldn't happen if the metals are coming from the same source. Nickel and iron have similar chemical properties and similar cosmic abundances. Seeing one without the other suggests they're being released through different processes, but at the temperatures and pressures in a comet's coma, there's no obvious natural mechanism that would preferentially release nickel while keeping iron locked in place. The leading hypothesis, proposed by several research teams, involves nickel-carbonyl compounds. These are molecules where nickel atoms are bound to carbon monoxide in a structure that's relatively fragile and can break apart under even weak sunlight. If the comet's surface contained nickel in carbonyl form rather than in metallic grains, it could release nickel gas at temperatures far lower than those needed to vaporize iron from more stable iron-bearing minerals. That explanation is plausible and fits within known chemistry. But it also raises the question of how nickel-carbonyl compounds would form in an icy body in the first place. In our solar system, the conditions required to create and preserve such molecules are rare. Finding them in an interstellar comet suggests that either the formation environment of 3I Atlas was chemically very different from anything in our local neighborhood, or there are processes happening in ancient icy bodies that current models don't account for. Dr. Avi Loeb at Harvard, who has spent years studying interstellar objects, pointed out publicly that nickel without iron is otherwise primarily associated with industrial refining processes on Earth. He suggested that the detection warranted consideration of non-natural explanations, not as a default assumption, but as a hypothesis worth testing, with the same rigor applied to natural scenarios. That position sparked debate within the astronomy community, with most researchers favoring natural chemical processes as the more likely explanation, but acknowledging that the nickel-iron anomaly remains genuinely puzzling. To address the question directly, a team of researchers pointed the Allen Telescope Array, a radio observatory designed to search for signals from extraterrestrial technology, at 3I Atlas and scanned across a wide range of frequencies. They were looking for any artificial radio emissions that might indicate the object was transmitting or had active electronics on board. The search came back negative. No artificial signals were detected at any frequency the array monitored. That doesn't conclusively rule out artificial origins, but it removes one of the most obvious signatures you'd expect if the object were technological. Combined with the fact that the outgassing behavior, while unusual, is still broadly consistent with natural comet activity, the scientific consensus remains that 3I Atlas is most likely a naturally formed object, with chemistry shaped by an ancient and unusual formation environment. The final unusual behavior came in late November 2025, as the comet was moving away from the Sun and beginning its outbound journey. Most comets, once they pass perihelion and start moving back into the cold outer solar system, gradually reduce their outgassing activity. The coma fades, the tail dissipates. The object becomes dimmer and harder to observe as the ices on its surface refreeze and activity ceases. 3I Atlas did the opposite. Even as it moved past the orbit of Mars and continued outbound, spectroscopic observations showed that it was still actively venting gas. The rate had decreased compared to its peak near perihelion, but the fact that it remained active at all at that distance was unexpected. Solar system comets occasionally show extended activity, but it's rare and usually associated with subsurface reservoirs of volatile ices that take time to heat up and vent. What made this particularly notable was that the outgassing composition had changed. Early observations near perihelion detected mostly water vapor and carbon dioxide. By late November, the dominant gas being released was carbon monoxide, a more volatile molecule that sublimates at lower temperatures. The shift suggested that as the surface ices were depleted by solar heating, deeper layers with different compositions were being exposed and beginning to outgas. This layered structure, where different depths in the comet contained different ice mixtures, told researchers something important about the history of 3I Atlas. It meant the object hadn't been thoroughly mixed or melted since it originally formed. The chemical layers preserved in its structure were like a geological record, each one representing a different stage in the environment where the comet accreted its material billions of years ago. By late December 2025, 3I Atlas had moved far enough from the Sun that most ground-based telescopes could no longer track it reliably. Webb made one final observation in mid-December, detecting methane in the outgassing for the first time, adding yet another data point to the growing chemical inventory of this ancient traveler. And then the comet faded from view, too distant and too dim for current instruments to study further. It's now moving outward at more than 150,000 miles per hour on a trajectory that will take it back into interstellar space within the next few years. It will never return. Barring some unexpected gravitational interaction with an object we haven't detected, 3I Atlas will spend the rest of cosmic time drifting through the space between stars, carrying its 12 billion-year-old ice and its unexplained chemistry with it. So what did 3I Atlas do that no other comet has ever done? It exhibited sustained multi-directional outgassing with chemically distinct jets that remained active far longer and at greater distances from the Sun than models predicted. It carried organic molecules that don't match any known comet chemistry database. It released nickel vapor without the corresponding iron that should accompany it. And it maintained activity on its outbound trajectory well past the point where solar heating should have shut down surface sublimation. Each of those behaviors, individually, has precedent in observations of unusual solar system comets. What makes 3I Atlas genuinely unique is that it displayed all of them simultaneously, in an object that formed in a completely different stellar system during a completely different era of galactic history. That combination gives planetary scientists their first detailed look at how comet chemistry can vary when the formation environment is radically different from our own. The findings don't overturn existing theories of how icy bodies form. They expand those theories by showing that the specific chemistry, the mixture of ices and organics, the isotope ratios, and the trace metal content can vary far more widely than solar system examples alone would suggest. Before 3I Atlas, every comet we'd ever studied in detail formed from the same disk of material that built our planets. This was the first time we could compare that local chemistry against a sample from elsewhere. And what the comparison revealed is that while the basic process of ice and dust accreting into comets seems to work the same way across different star systems, the details matter. The temperature, the radiation environment, the chemical composition of the surrounding gas and dust, all of those factors leave signatures in the final object that we can now read if we have sensitive enough instruments. The next interstellar visitor, whenever it arrives, will add another data point. The Vera Rubin Observatory in Chile, which began full operations in 2025, is expected to detect dozens of interstellar objects over the next decade. Each one will carry its own chemical fingerprint from its own formation environment. Over time, those measurements will build into a genuine sample set of planetary system chemistry from across the galaxy. 3I Atlas was a preview of what's coming. It showed us that interstellar objects aren't just interesting curiosities. They're direct physical samples from other star systems, carrying information about planet formation processes that we have no other way to access. Every molecule detected, every isotope measured, every unusual behavior observed adds to the map we're building of how planetary systems form under different conditions in different parts of the galaxy. Here's what you should take away from this. 3I Atlas displayed outgassing behavior, chemical composition, and sustained activity patterns that don't match any solar system comet we've studied. The nickel without iron remains unexplained at the molecular level. The organic molecules detected don't fit standard databases, and the 12 billion year age of its ice makes it the oldest confirmed material ever observed passing through our solar system. None of that makes it alien technology. What it makes it is a naturally formed object from a genuinely alien environment, shaped by chemistry and physics that operated under different conditions than anything in our local history. And that's extraordinary enough without needing to invoke non-natural explanations. If this kind of straight-talk science coverage is what you're looking for, subscribe to Space Horizon. We cover space discoveries as they actually unfold, with all the complexity and uncertainty that real science involves. Drop a comment and tell me which finding about 3I Atlas surprised you most. The age, the chemistry, the nickel anomaly? Next time, we're covering what Voyager 2 detected at the solar system boundary that Voyager 1 completely missed, and why that finding changed our understanding of the heliospheric structure. Thanks for watching. I'll see you at the next horizon.